Welcome, General Chemistry Gang. In this lecture, we're getting into the second part of Chapter 17. Talking about aqueous, ionic equilibria. And so we've already talked about buffers and how buffers can maintain constant pH. We've also talked about how buffers maintain that constant pH through, even with the addition of strong acid or strong base, and that's what we covered in the earlier videos from this section. And so now in the second part of this, we're talking now about titrations. And titrations are basically, this is a method used to determine unknown concentrations of a particular molecule. There are, acid-base titrations. And that's what we tend to focus on within this section. But there are also others. So that's, one of the main things that we see a lot with the use of the titration is to determine an unknown concentration. We tend to use a lot of acid-base chemistry for those types of titrations, but we can also use gaining or loss of electrons, such as in redox chemistry, a topic that's coming up much later. We can also use that as a way. Also, this is also a method for the determination of, certain physical properties such as Ka or pKa, Kb or pKb, or even molar mass. So we utilize this for unknown concentrations, but let's say I made a new molecule in the lab, and that molecule is an acid, or that molecule is a base. And so I could further characterize that particular molecule by measuring its Ka or pKa, as well as if it was a base, its Kb or its pKb. Also, molar mass being a very important determination of, the molecule that you actually thought you were making in terms of a physical property of it. So with titrations, what do we need? Well, we need a quantitative reaction. And so to ensure a quantitative reaction, one of the starting materials needs to be strong, or very reactive. We need the one to be strong because we need 100% conversion. And that allows us basically to relate moles of a known starting material that is strong 2 moles of an, unknown starting material. All right, remember, titrations are used to determine an unknown concentration, right, of a material. So we have a known starting material, and that's always going to be strong. Being strong is going to allow us to have that 100% conversion, that desire for the quantitative reaction, and that allows us to relate moles of the known starting material now to moles of the unknown. And so that allows us to now quantitate or determine the unknown concentration that we would be looking for. As an example of that, we could look at 2 very strong species, such as hydrochloric acid and sodium hydroxide. Right, HCl is our strong acid. Remember, a strong acid is that source of H plus or hydronium ion, right? Complete dissociation. And sodium hydroxide is our strong base, right? This is a metal hydroxide, so a direct source of OH minus. And when they react, right, they're going to react to make water. They're being neutralized as well as sodium chloride. So this is that neutralization reaction. The H plus and the OH minus react, right, and we're neutralized to basically make our H2O. So since both of these are very strong starting materials, strong acid, strong base, that's why we have 100% conversion. So I can relate moles of HCl directly to moles of H2O or sodium chloride, and I can do the same thing with sodium hydroxide. So that's the first thing that we need in terms of a titration, is we need basically a quantitative reaction. The second thing, which I hinted to above, is the necessity of a strong titrant. A strong titrant is a strong, right, or very reactive starting material whose concentration is accurately known. This is usually done or usually determined in a separate reaction or process. So the titrant, we really know that concentration, and it's also very strong. So it's a strong starting material, and its concentration is accurately known. This allows us to relate it to moles or molarity of then the unknown that we're actually trying to determine. So if I am titrating a weak acid, I would want to use a strong base titrant. Often sodium hydroxide is used for that type of strong base titrant. Or if I'm titrating a weak base, I would want now a strong acid titrant. Oftentimes HCl is a common choice of strong acid titrant. Now I say titrating a weak acid or weak base, but realize that this could also be titrating of a strong acid or strong base. So we're not limited to what we're titrating. What we are limited to is the actual titrant, what has to be strong to ensure that quantitative process. So we need to have that strong titrant as well. The other species that we need within the titration is the indicator. And the indicator is a chemical dye whose color is pH dependent. So at 1 pH, you have, one color, let's say yellow, and at another pH, you have a different color. Let's say blue. And so this is just a way to visualize. And it's a visualization tool for the equivalence point determination. So that's why we use it. We'll get into what the equivalence point actually means, but we need to have, not only this quantitative reaction, the strong titrant, we need to have an indicator to also view the actual process as far as changing of color to kind of indicate this notion, this new notion of the equivalence point. All indicators have a pKa, and their color changes at a pH that is essentially equal to the pKa. So you have a pH of the titration, the titration equivalence point, and the indicator, that's your pKa. So right around that pKa is where we have the color change occurring. So we want to pick an indicator whose color change occurs right around the equivalence point and the pH of that equivalence point. So the indicator pKa that allows for a visual, remember that visual is the color change. So visual of the equivalence point right? That pKa needs to be plus or minus 1 unit around the pH of the equivalence point. So if I have an equivalence point pH equal to 5.6, that means that my indicator of choice its pKa would be anywhere from 4.6 to 6.6. And it's within this range that we see the color change actually occur. So it's almost like we do two titrations. One is the titration of the unknown, and the other is kind of the titration of the indicator, which once we get to its pKa, all of a sudden has this color change. And we want to make sure that that choice of indicator is going to change colors right around that equivalence point. So what is the equivalence point? The equivalence point is when during the titration moles of the strong titrant is equal to moles of the unknown molecule. Right? This is a mole game, right? That as we're doing the titration, we're going to start to increase and increase moles of our strong titrant. And eventually we'll get to a point when the strong titrant moles is equal to the moles of the unknown molecule. That's our equivalence point, and that actually now allows us to relate moles of the strong titrant to moles of the unknown. So that allows us basically to determine the unknown concentration that we're looking for. So that's the most important region that we tend to see in the determination of an unknown concentration is the equivalence point. This is also an area where molar mass is determined. So at the equivalence point is where we can determine the unknown concentration, but also we could use it to determine molar mass. As far as Ka or Kb or pK or pKb, they're actually determined at another region of the titration, which is something we'll get into later on. The last piece of the titration is the titration curve, or pH curve, or pH, plot, right? There's a number of ways to say that. But basically a titration curve. And all a titration curve is a plot of volume of strong titrant versus pH. So on the x-axis, we have our volume of titrant. Remember, with our strong titrant, we have known concentration. So if we have volume and we have concentration, we have access to moles, right? Bringing both of those two ideas together. And then on the y-axis, we have pH. And then we can have different plots as far as that's concerned. You know, we can have plots that might look like this, and that would be an example of a strong base titrated with strong acid, or we could see other types of plots, such as maybe something that looks like this, and this would be a strong acid titrated with a strong base. So in red, we're titrating a strong base, so in the beginning we're very basic, or above 7, and then as we get closer to the equivalence point, we see this very vertical line happening. And so that's where we tend to visualize the equivalence point, is in that region in the middle. And then once we're past the equivalence point, now we'll tend to have excess of the strong titrant, which will be strong acid, and that's why we have a very low pH at the end of that titration curve for the red plot. For the purple plot, we have the opposite. We're titrating a strong acid with a strong base. So in the beginning, all we have is acid, and that's why we have a very low pH. Then we have a huge increase right around the equivalence point. And then now that we are past the equivalence point, now we find that we'll have excess of the titrant or the strong base. And now we're in that basic region. We'll get more into the plotting later with specific examples of not only strong types of titrations, as far as strong acid, strong base types of titrations, but also getting into weak acid and weak bases and how we can titrate them using strong base titrants and strong acid titrants. That's the topic of the next lecture.